First, I would like to welcome you to this webinar sponsored and hosted by the Federal Highway Administration and the University of Nevada at Reno. The FHWA has an ongoing accelerated implementation and deployment of pavement technologies program, which includes deployment of innovative technologies to improve pavement performance and reduce agency risk. This presentation or webinar topic under this program is focused on the advances in design and construction of stone matrix asphalt mixtures. The presentation was prepared by Harold Von Quinnes and Praveen Gopasetti of Applied Research Associates, and is being delivered under the Development and Deployment of Innovative Asphalt Pavement Technologies Cooperative Agreement between the University of Nevada in Reno and the Federal Highway Administration. The webinar is being delivered by Harold Von Quinnes of Applied Research Associates. FHWA requires a statement or notice to be given at the beginning of all webinars under FHWA sponsorship. This is the first part of the notice. I will give you some time to read the notice in total that is included on this slide. This slide includes a continuation of the notice from the previous slide. I'll give you some time to read the two paragraphs of this notice in total. The presentation is arranged into 5 sections. The first section is the introduction that will present basic information and definitions on SMA, which includes the background information on SMA mixtures. The second part is a summary of the advancements in design and construction of SMA mixtures, as well as a summary of the performance history of SMA mixtures from their inception into the U.S. The third part is a tie between SMA mixtures and the balanced mixture design process. The fourth part is a tie between SMA mixtures and structural pavement design via mechanistic-empirical design procedures. The fifth and final section is a summary of takeaways from the webinar itself. Beginning with the introduction. A technical brief on this topic has been published through the Federal Highway Administration. The location for downloading the technical brief is provided on this slide. First, I'd like to start with a historical perspective of SMA mixtures since they were introduced into the U.S. in the 1980s. The chronological order of important events related to SMA mixtures are listed or noted on this slide. The SMA mixtures were first introduced or imported from Europe into the U.S. in the 1980s. There was a European study tour that was held in 1990 that overviewed the SMA mixtures and their performance characteristics from Europe. The SMA technology imported into the U.S. From Europe resulted in many meetings, especially after the European study tour in 1990, in many meetings and sessions on SMA mixtures, both locally and on a national perspective level. The first SMA International Conference in the U.S. was held in November 2018. There have been many publications on SMA mixtures. NAPA produces a heavy-duty pavement or high-stress mixture application, of which SMA mixtures are an important part in that NAPA publication. More importantly, however, the most important historical perspective is that for 30 years, SMA mixtures have provided excellent performance on high-stress, heavy-duty, or high-volume roadways. For SMA mixtures, the key is to provide stone-on-stone contact with excellent internal friction so the mixture is not susceptible to lateral flow and resist plastic deformation. SMA mixtures, also called stone mastic asphalt, are basically gap-graded blends which result in stone-on-stone contact when the gradation is adequately designed. They have a rich mortar binder with a stabilizing agent and mineral filler. They're compacted to a low air void content, and from that, they exhibit very high internal shear strength. The high asphalt content provides excellent durability of the mix, and the mineral fibers and polymer-modified asphalt provides excellent resistance to fracture and crack deterioration, even after a crack occurs in the SMA mixture itself. The photos in this slide shows cut sections of different cores. The cut section on the left is of an SMA mixture, and the cut section on the right is of a dense graded asphalt mix itself. As shown in the SMA core on the left, that illustrates the stone-on-stone contact for SMA mixtures. Some conventional mixtures, as shown on the right, the core on the right, can have some stone-on-stone contact, but they generally have lower asphalt contents by weight and are not as durable. In many cases, however, the larger aggregate particles basically flow in a sea of fines for some of the well-graded mixtures itself. SMA mixtures are comprised of 70 to 80% coarse aggregate, 8% to 12% filler, 6 to 7% asphalt binder, 0.3% cellulose, and 0.3 to 0.4% mineral fiber. The cellulose and mineral fiber prevents or reduces asphalt drain down. The higher asphalt content compared to conventional dense graded mixes increases the compliance of the mixture, reducing the probability for thermal cracking, and also increases the resistance to fatigue cracking. Some use of polymers as stabilizing agents are also included in SMA mixtures, which also increases durability and increases the resistance to cracking and rutting. SMA mixtures in heavy-duty asphalt pavements are not new and have served well for years. These heavy-duty asphalt pavements, or where SMA mixtures have been placed and have exhibited excellent performance, have been on high-volume interstate routes, truck-designated haul routes for selected commodities, and on various airfield, some of the taxiways, runways, aprons, and air cargo facilities. This slide includes a map of the U.S. showing the usage of SMA in the U.S. The 18 states highlighted in solid green routinely use SMA mixtures, mostly on state and interstate routes with very heavy or high traffic volumes. The performance of these has been very good in general. This slide shows a bar chart graphical comparison of the total tonnage of SMA mixtures versus superpave dense graded remixes that have been reported by some agencies. SMA mixtures are only used for the wearing surface, while the superpave polymer modified dense graded mixtures are and can be used for other asphalt layers, so the tonnage is greater for the dense graded mixes in comparison to the SMA mixtures. SMA mixtures are not typically used as a base mixture or as an intermediate asphalt layer. They're primarily used for the wearing surfaces. Based on performance studies summarized on this slide, many agencies' records show a significant improvement in the service life of SMA mixtures over superpave dense graded mixes. This slide summarizes the service life of flexible pavements reported by different state Department of Transportation. As shown, those that are highlighted in yellow, the SMA mixtures have significantly greater or longer service lives. The other reported studies that are not highlighted, the superpave mixtures have slightly greater service lives, but it's not considered to be significantly longer service lives. In fact, the superpave mixes where for those agencies that have reported longer service life, the average is slightly less than 1 more year of added service life. Conversely, the average added service life for the other agencies that have reported higher service lives for SMA mixes is almost an average of 6 additional years of service life for SMA mixtures compared to the superpave mixes. For composite pavements, the cells highlighted in yellow show those studies or Department of Transportations that have reported SMA mixtures to have longer service life in comparison to the superpave dense graded mixes. As shown, the studies reported SMA mixtures have significantly higher service life in comparison to superpave mixes on composite pavements. Only one study, which was the Pennsylvania DOT on interstate pavements, reported a slightly longer service life for the superpaved dense graded mixes compared to SMA mixtures. However, it's an average of only slightly more than 1 year service life for the superpaved mixes. Conversely, the added service life reported by the 5 other agencies reported more than 6 additional years on the average of higher or longer service lives for SMA mixtures compared to their superpaved dense graded mixtures. This slide is simply a summary of the previous 2 slides as illustrated. SMA mixtures have lasted longer in comparison to dense graded superpaved mixes. In general, 4 out of 7 flexible pavements with SMA surfaces exhibited longer service lives, and those were significantly longer service life. The 3 out of the 7 for the superpaved mixtures that had longer service lives were only slightly greater service lives. For the composite pavements, 5 of the 6 studies reported significant increases in service lives of the SMA mixtures as compared to the superpaved dense graded mixes. Continuing with a comparison of SMA and conventional dense graded mixes, this slide illustrates a graphical summary of data collected by the Colorado Department of Transportation showing the cracking in the asphalt overlays of rigid and flexible pavements of SMA mixes versus conventional dense graded mixes itself. With the slide on, or the graph on the left, the dense graded neat asphalt mixes exhibited much more transverse cracks in a 1/10 of a mile basis as compared to the SMA and or polymer modified mixes over time. The graph on the right are the asphalt overlays of flexible pavements. In general, the dense graded neat asphalt mixes exhibited higher number of transverse cracks in a 1/10 of a mile basis compared to the SMA, PMA wearing surfaces, but eventually at 10 years, the amount of cracking became equal as reported by the Colorado Department of Transportation. In summary, or in general, there is a delay and or lower number of transverse cracks in SMA overlays compared to conventional dense graded mixes. A more important observation, however, that is not illustrated in these 2 graphs is the crack deterioration between SMA mixes and conventional dense graded mixes when cracks do occur. The crack deterioration is illustrated on the next slide, or the difference between the crack deterioration between the 2 mixture slides will be illustrated on the next slide. SMA is considered a much tougher mixture preventing crack edge deterioration. The observation on crack deterioration were taken from a study in both Colorado and in Washington, as well as in other agencies by the presenter. The transverse cracks exhibited in conventional dense graded mixes, as shown by the photograph, exhibit more severe crack deterioration along the edges of the transverse cracks. while in the SMA mixtures, as shown by the photograph in the lower right, the SMA mixtures, the cracks or transverse cracks remain basically hairline without significant crack deterioration. The reports are documented for these two studies are listed on this slide. Another advantage of SMA mixtures is noise reduction in comparison to conventional dense graded mixtures. As shown in this slide, the dense graded asphalt mixture noise level is included as the reference. So the decibel level or difference in the decibel level is considered 0. The Portland cement concrete surface has or is noisier or has a higher noise level of 3, on the average 3 decibels. Conversely, the SMA mixtures, as shown in the highlighted row, has a 2 decibel lower noise level in comparison to the dense graded asphalt mixture. In comparison, open graded friction cores have a 4 decibel level lower noise level in comparison to the dense graded asphalt surfaces. So SMA as well as open graded friction courses are generally quieter than the standard dense graded asphalt mixtures on the surface. The photograph on the upper left shows the coarse surface texture of the SMA or the macro surface texture of an SMA surface as compared to the macro surface texture of a dense graded surface itself. The macro surface texture is one of the reasons for the lower noise level in comparison to the dense graded asphalt surface. Performance studies have shown SMA mixtures are tough and are rut-resistant mixes that have exhibited excellent performance. So one of the questions that gets asked is, what are the reasons for this excellent or better performance, and how has it changed or improved over time? Some reasons for the excellent performance of SMA mixtures include better material requirements, better mixture design requirements, more torture testing or mechanical testing requirements to measure the engineering properties of the SMA, as well as better production construction requirements itself. In the presenter's opinion and observations from other performance studies, SMA mixtures consistently exhibit lower rut depths, less cracking, which includes predominantly top-down fatigue cracking and transverse cracks, and much less crack deterioration along the edges of the crack when they do occur. In fact, that is a very significant benefit of SMA mixtures for reducing crack deterioration as compared to conventional dense graded mixtures. Now let's move to section 2, or the second part of the presentation, on looking at the advances that have been made in design and construction of SMA mixtures themselves. This slide lists some of the publications and standard practices for the design and construction of SMA mixtures. AASHTO R4608 and AASHTO M325-08 are the more common methods and specifications that have been used and are being used by many agencies for designing and placing SMA mixtures in the U.S. AASHTO T305-14 is also a very important test method for determining the potential for drain down characteristics in uncompacted asphalt mixtures. As I mentioned earlier in the presentation, NAPA has an informational series referred to as a Quality Improvement Series number 123 on the design and construction of heavy-duty pavements for high-stress applications. The second edition, which was published in August 2019, was prepared by both Harold von Quennis and Charles Hughes. In the NAPA publication, heavy-duty pavements are defined as shown on this slide. Pavements and asphalt mixtures supporting extreme loading conditions. Extreme loading conditions can consist of large wheel loads, high tire pressures, unique tire configurations, slow-moving or static loads, and/or an excessive number of loads going well beyond standard pavement and asphalt mixture design procedures. The NAPA publication, Quality Improvement Series 123, can be downloaded from the website shown on this slide. This is a listing of some of the SMA mix design procedures being followed by selected agencies. Most agencies are following AASHTO R 46-08. This slide summarizes the selection criteria and policies for SMA mixture use for selected agencies as shown on the slide. The selection criteria and policies, however, do vary by agencies. SMA certainly is more expensive, simply because of the higher asphalt contents, the more durable aggregate requirements, and the inclusion of fibers and modified asphalt binder. From different agencies, there is no consistent conclusion comparing cost effectiveness of SMA versus dense graded mixes. However, many agencies, but not all, have found SMA mixtures to be cost effective as compared to conventional dense graded mixes. The cost effectiveness issue will be discussed in greater detail in a latter part of this presentation, but under this section or part of the presentation. This slide summarizes some of the unit bid prices, which affects the cost effectiveness of different mixes for SMA mixtures in terms of the percent higher unit cost in comparison to conventional dense graded mixes for selected agencies. The reason for the higher unit bid prices is related to the material requirements that were previously mentioned on the previous slide, as well as on this slide, and the amount of asphalt binder added to SMA mixtures. Just about all agencies have reported that SMA mixtures are consistently higher in terms of initial cost than for conventional dense graded mixes because of the higher binder contents, more durable aggregates, inclusion of fibers and polymers, limitations when using special aggregates in coal feed bins, and shortened paving windows due to traffic control itself. The relative difference between a 5-year average unit bed price of SMA and conventional dense graded surface mixtures for the same traffic level shown in the bar graphs are from 2011 to 2015. Overall, or the relative performance difference between the 5-year average weighted bid price of SMA and conventional dense graded mixes for the traffic level between 2011 2015 are shown in an expanded version in this slide from the previous slide. Overall, SMA mixtures are about 25% higher in terms of the initial mixture cost in comparison to conventional dense graded asphalt mixtures. So in terms of economic considerations, other factors also contribute or have been used to try to reduce the higher cost of SMA mixtures. One typical and common feature or added material component to reduce the cost of SMA is to use reclaimed asphalt pavements or RAP and or reclaimed asphalt shingles or RAS in the SMA mixtures itself. Other agencies do not permit RAP to be added to the SMA. The bar graph shown on the left is the average cost difference in dollars per ton between SMA and dense graded mixes for those states shown that do allow RAP and RAS in the SMA mixtures. The bar graph on the right shows the cost difference in dollars per ton between SMA and dense graded mixes for those agencies that do not allow RAP and RAS in SMA mixtures. Overall, there is a $6 to $31 ton cost difference for those states that allow RAP-RAS in SMA as compared to a cost difference range of $12 to $28 per ton for those states not allowing RAP in the SMA mixes itself. As an example, Georgia Department of Transportation allows only 15% RAP for SMA, while it also allows up to 40% and 25% RAP for conventional dense graded mixes in continuous and batch plants, respectively, as shown on the slide. This slide simply shows an expanded version of the bar graphs on the previous slide. Those agencies that do allow some percentage of RAP in the RAS, there is a reduction in the material cost in comparison to those agencies that do not allow RAP and RAS in SMA. In general, those states that do not allow RAP or RAS, the cost difference between SMA and dense graded mixes is about $21 per ton on the average, in comparison to an increase of only $17 per ton on the average for those states allowing RAP and RAS in SMA. The important question to be asked is will the RAP and or RAS in the SMA have an impact and or reduce the service life of the SMA mixtures, or reduce the difference in the service life between SMA and the dense graded mixes that were presented earlier in this presentation. This slide summarizes the findings from 3 agencies relative to the cost effectiveness of SMA mixtures in comparison to conventional dense graded mixes. As shown, 2 agencies have found SMA mixtures to be cost effective, while only 1 agency has not reported SMA to be cost effective. The cost effectiveness is related back to the average service life difference between SMA and conventional dense graded mixes, which will be illustrated on the next slide. Relative to this slide, SMA has a higher net present value for the Michigan DOT, but not a cost-effective alternate. For Virginia and Maryland, the higher cost of SMA is justified by the greater pavement life extension or higher service lives in using SMA mixtures. This slide, as noted previously, includes information from the previous slide, but in an expanded version. Many agencies, not just those listed here, show SMA have longer service lives but higher initial material cost. The cost effectiveness of SMA is heavily dependent on that difference in the service life itself between SMA and superpave or conventional dense graded mixtures. Maryland and Virginia have reported SMA to be cost effective, while Michigan has not found SMA to be cost effective in comparison to conventional dense graded mixes. The reason for that finding or observation comes back to the difference in service life. The service life difference is shown in the first 2 columns for Maryland, Michigan, and Virginia. Michigan only reported a 1-year extended service life above dense graded mixes for the SMA mixtures. However, Maryland reported 8 additional years of service life, and Virginia has reported 10 additional years of service life for SMA mixtures. The unit cost, the average unit cost or difference between SMA and dense graded mixes are shown on the average under unit cost. Maryland, there's a $10 additional per ton of mix for SMA compared to superpave. Michigan has a $16 added cost or per ton for the SMA mixtures, while Virginia has an added cost of $25 per ton on the average for SMA mixtures in comparison to the superpave mixes. The net present value is shown on the columns to the right. There is a $7 per ton reduction in net present value for the SMA mixtures as compared to the superpave because of the longer service life. So it's cost effective. The Virginia report on the average shows a $16 per ton reduction in net present value for SMA mixtures compared to superpave, while the Michigan data showed a $9 per ton added net present value for SMA mixes compared to superpave. So Maryland and Virginia where SMA was found to be cost effective, while Michigan found the SMA not to be cost effective. The reason for that is the only one additional years of service life of the SMA mixture compared to the superpave dense graded mixtures. A key question is, why the difference between the agencies? An answer to this question is going to come back to the definition of SMA mixtures, which will be discussed and answered in the following slides of this section. In other words, explaining why some agencies have found SMA not to be cost effective, at least a few agencies, as compared to many more agencies that have found SMA mixtures to be cost effective. First, there is no question that SMA mixtures are much more resistant to plastic deformation because of their high internal friction resistance from the stone-on-stone contact of a gap-graded mixes. This is illustrated in the figures or photographs shown in this slide. The grooves sawed in SMA mixtures in the center photograph along a runway have held up significantly longer than grooves sawed in traditional dense graded mixes, shown on the photograph on the right in terms of a close-up, even though the amount of asphalt is higher, significantly higher in the SMA mixtures. The grooves remained intact for most part of the under heavy loads, while the grooves cut or sawed in the conventional dense graded wearing surface of roadways have collapsed over a shorter period of time. The reason for this, as previously noted, has to do with the internal strength of the SMA mixtures from stone-on-stone contact itself, resulting in very high internal frictional resistance. In addition, there has been an NCAT research study on SMA performance. Some 86 SMA pavement projects have been monitored across various states over the short term and long term. Performance has been reported as good to excellent, with very few reported issues. So SMA mixtures from the NCAT research study has outperformed standard dense graded asphalt mixes for both rutting and cracking resistance after being in service life for 2 to 6 years. Additional or other studies have found that to be the case for over 10 years of performance. In fact, over 90% of the SMA projects had rut depth measurements less than 4 millimeters, or about 0.15 inches, and there was no evidence of raveling on the SMA projects. There have been some reported issues of fat spots due to segregation, low voids in the mineral aggregate, some drain down, and or higher asphalt contents with SMA mixtures. NCAT and other agencies have investigated reducing the material and aggregate requirements to make SMA mixtures more cost competitive from an initial construction or material standpoint. So there have been studies trying to low cost an SMA mixtures or produce SMA mixtures that are cheaper to make them more cost effective. So an additional question is, making the mix cheaper, what impact does that have on the service life? Performance data has been collected on 19 SMA sections at the NCAT test track. Different aggregate sources have been used, but that had no significant impact on performance. The graph shown on the right, the red diamonds are basically the IRI values in terms of inches per mile measured over cumulative equivalent single axle loads, while the blue squares show the mean texture depth over that same time period. So roughness and mean texture depth measurement showed no change in surface characteristics throughout the 2-year testing cycle of different SMA mixtures that have been designed, constructed, and produced as SMA mixtures. A notable example from the NCAT study was a section paved with a 12.5 millimeter nominal maximum aggregate size for an SMA mixture with granite aggregate and 28% flat and elongated particles at a 3:1 ratio. The findings on that section that after more than 10 million equivalent single axle loads less than 5 millimeters or 0.19 inches rutting was observed, and there was no evidence of cracking on that section. So SMA mixtures have been good, performance has been good, and have resulted in cost-effective mixes. The question that always gets asked, as mentioned previously, how do or can we reduce the initial cost of SMA, or how do we make them cheaper to be more cost-effective? As an example, do we remove fibers, or can we remove fibers? Can we reduce the aggregate requirements? Can we reduce the asphalt content? Can we reduce the asphalt requirements and other such items in the SMA mixtures without having a significant impact on the service life and or performance of those mixtures? There have been studies comparing projects between a standard SMA mixture and then making reductions either in terms of asphalt content, removing fibers, removing the polymer modified asphalt on adjacent sections to determine the difference in performance as well as the difference in cost between projects defined as SMA and other SMA mixtures that are called SMA mixtures but not designed to the strict requirements as previously mentioned during this presentation. Fiberless SMA mixtures has been placed on 2 pilot projects in the U.S., Route 1 in New Jersey. The finding from that study, there was a reduction in production temperature going to 275 to about 285 degrees Fahrenheit, which reduced drain down by not having fibers. There was also a reduction on oxidation by lower production testing, and thus reducing the increase in stiffness and brittleness as opposed to mixtures produced at higher temperatures. Some of the benefits are cost-effective due to no fiber, low energy consumption, increase in haul time, and lower environmental impact. There has been positive short-term performance on some of these projects where the SMA requirements have been reduced or minimized. But most long-term observations do indicate a reduction in service life as compared to the SMA mixtures with the strict material requirements or stricter material requirements. This slide shows an example of truck-to-truck segregation, longitudinal segregation, and bleeding or flushing reported on some SMA mixtures with reducing or relaxing the aggregate material requirements and or not using fibers or not using polymer modified asphalts. It's been the presenter's experience that these projects exhibit more cracks, much more severe crack deterioration, higher raveling because of the segregation, and higher levels of rutting. Some of these mixtures have been called SMA, but would not be categorized as SMA based on the aggregate requirements, excluding fibers, and using lower asphalt contents. In fact, there's been further investigation of these SMA mixes found that they were SMA in name only, no fibers or mineral filler, no polymer modified mixes. These mixes have exhibited lower service life, and is a reason why some agencies have reported SMA mixtures to have a higher life cycle cost or not be cost effective in comparison to conventional dense graded mixes. One reason is the lower service life of these name-only SMA mixes that do not have the fibers or mineral filler or the polymer modified asphalt and higher asphalt contents with the fibers and with the polymer modified mixes. So one needs to be careful in reporting studies of SMA mixes that are not found to be cost effective to ensure that those are really true SMA mixes with the same material requirements in the AASHTO mix design test standard. Overall, or in summary, SMA mixtures with the aggregate requirements, fibers, and higher asphalt contents as originally defined by the AASHTO standards and specification have exhibited excellent performance and or cost effective. In other words, they do exhibit lower life cycle cost in comparison to conventional dense graded mixes, even when used on high volume interstate routes, truck designated haul routes for selected commodities, and on different airfields facilities such as taxiways, runways, apron, and other air cargo facilities as mentioned earlier in the presentation. So SMA mixtures and heavy-duty asphalt pavements are not new, but have exhibited excellent performance and have served well for years. Now, starting section 3 on SMA mixtures and the balanced mixture design process. As per AASHTO PP 105-20, the balanced mixture design process is described as asphalt mixture design using performance tests on condition specimens that address multiple modes of distress by considering mix aging, traffic, climate, and location within the pavement structure. However, AASHTO PP 105-20 is a non-binding standard and not considered a federal requirement on federally funded roadways. The balanced mixture design approach, however, provides several benefits, such as enhanced quality and longevity, stronger tie between design elements and field performance, mixes using more alternate and recycled materials, industry innovation to meet performance goals. AASHTO standard practice describes 4 approaches for the balanced mixture design method that are listed on this slide. Approach A requires full compliance with the existing volumetric requirements, but additional performance requirements, and is considered the most conservative approach. Approach B requires compliance with the existing volumetric requirements at the preliminary optimum binder content, but allows moderate changes in asphalt binder content for performance observation based on mixture performance test results. Approach C allows some of the volumetric requirements to be relaxed or eliminated as long as the performance criteria are satisfied. It is a less conservative approach, or considered a less conservative approach. Approach B has no requirement on volumetric properties and relies solely on mixture performance test results for the mix design optimization and determining the optimum binder content. It is also the least conservative approach among all of the other approaches. The balanced mixture design method uses 3 types of tests, which are noted on this slide. Rutting test, or distortion-based test, are used to evaluate the susceptibility of asphalt mixture to plastic deformations, or their deformations or displacements that are not recoverable under wheel loads and in the environment. Cracking or fracture-based tests are used to evaluate the susceptibility of the asphalt mixture to cracking under wheel loads as well as under environmental loads. Moisture damage or durability tests are used to evaluate the susceptibility of the asphalt mixture to changes in its responses to water or moisture, which includes deformation and or fracture. It is important to understand how material properties are measured and the importance of the testing conditions for understanding and using the test results themselves. 3 states, Illinois, Louisiana, and Texas Department of Transportations, have added performance testing to their SMA mixture design procedures as part of their implementation efforts for the balanced mixture design approach or method. The table in this slide shows the performance test requirements considered by these 3 agencies themselves. For cracking, flexibility, index test, the semicircular bend test, and overlay test were considered, and for moisture damage, tensile strength, loaded wheel tester, and the Hamburg wheel tracking test are also considered. The Hamburg wheel tracking test and the loaded wheel test are also considered for rutting. Aggregate gradation is one of the more important factors in the balanced mixture design process to establish the job mix formula. This slide simply shows the types of different aggregate gradations. SMA is typically considered a gap-graded and only has a small percentage of particles in the mid-range particle size. As shown in the figure, the curve is flat in the mid-range, in the mid size range of the aggregate particles. Gap-graded aggregates are used to obtain uniform textures in exposed aggregate concrete, and close control of mixed proportions is necessary to avoid segregation. Because the aggregates are all in contact, rut resistance relies on aggregate properties rather than the asphalt binder properties to a large degree. Comparing gap-graded to other mixtures, the dense-graded or well-graded aggregate gradation, shown in the dashed blue line, has gradations close to the FHWA maximum density curve. In other words, it typically has lower voids in the mineral aggregate, and then requires lower asphalt content. It refers to a sample that is approximately of equal amounts of various sizes of aggregates. By having a dense gradation, most of the air voids between the materials or particles are filled with aggregate particles. As shown in the figure, a dense gradation will result in an even curve on the gradation graph itself, resulting in lower voids in the mineral aggregate and requiring lower asphalt contents. An open graded aggregate blend contains only a small percentage of small-sized particles. This results in more air voids and much higher voids in the mineral aggregates because there are not enough small particles to fill in the voids between the larger particles. The open graded relationship is shown by the dashed black line. The curve is near the vertical in the mid-size range and flat and near zero in the small size range. The gap graded has higher voids in the mineral aggregate, requiring higher asphalt content to the same design air void level in comparison to the well-graded aggregate blends. SMA mixes are mostly placed as wearing surface courses on high-volume roadways. Based on test findings, it has been found that using SMA mixes as a wearing surface is beneficial over intermediate layers and base layers, resulting in higher stability, higher stiffness, higher density, higher relaxation, higher tensile strength, but lower permeability. It was also observed that use of SMA mixes as a base layer will result in higher fatigue strength, but SMA mixes are typically not used in a base layer. Now let's move to section 4, which is on SMA and mechanistic empirical based design procedures. Critical mixture properties measured in mechanistic empirical based structural design procedures are shown in this slide. Asphalt mixture properties include high stability and stiffness to resist deformations, high compliant or ability to withstand sustained wield and thermal loads, higher strengths to resist or withstand cracking, higher fatigue resistance or the ability to bend without cracking on multiple cycles, or durable or the ability to withstand moisture damage. In support of the use of mechanistic empirical based methods, some state Department of Transportation, for example, Colorado, Pennsylvania, Utah, and Wisconsin, have sponsored test programs to measure the asphalt properties of SMA mixtures. Properties measured on SMA mixtures include dynamic modulus, for predicting rutting and fatigue cracking predictions, repeated load plastic strain for predicting rutting, indirect tensile creep compliance and strength for predicting low temperature or transverse cracking, and also top-down fatigue cracking. SMA is mainly placed on the wearing surface, so bottom-up fatigue cracks are not always applicable to SMA mixtures themselves. Performance observations are needed to ensure that a mechanistic empirical based design method is predicting the stresses for the SMA and other asphalt mixtures without bias. The distress observations made for flexible pavements confirm that SMA mixtures do exhibit lower levels of rutting, lower levels of transfer cracking and crack deterioration, lower levels of top-down fatigue cracking, and hence have lower levels of IRI or are more smoother. Some examples of these observations on data collected by one specific agency, the Pennsylvania Department of Transportation, reported and showed the average rut depth of SMA was 0.37 inches compared to average rut depths of 0.4 inches for super paved mixes. Within that same study, the average alligator cracking of SMA mixes was 2.4% compared to 7% for super paved mixes, which is a significant reduction in alligator cracking. The average length of transverse cracks of SMA mixes was found to be 581 feet per mile compared to 1,144 feet per mile for super paved mixes. Also, a significant reduction in the length of cracks for SMA mixtures. Mixture design improvements for all asphalt layers and structural design adequacy for all pavement layers are the main reason for improved pavement performance using SMA mixes on heavy volume pavements. There have been mixture design improvement for all layers. Also, structural design adequacy of all layers is a critical item to consider. But both of these have resulted in very good pavement performance where SMA mixtures have been used as wearing surfaces. It should also be noted that SMA mixes should not be placed over a weak or inadequate structure and expect good or excellent performance. The pavement is a system, and all layers, including foundation layers, must be designed adequately and constructed adequately. All can have a significant impact on pavement performance, and simply placing a tough, durable SMA mix over an inadequately placed aggregate base and or subgrade will not ensure long-term performance. Now, what are the reasons for differences in mixture properties between SMA and dense graded mixes? This can be due to differences in the test results observed for dynamic modulus, repeated load plastic deformation, indirect tensile creep compliance, and indirect tensile strength as required by mechanistic empirical design procedures. In summary, dynamic modulus values for SMA mixtures can be higher or lower in comparison to conventional dense graded mixtures because the dynamic modulus is measured in accordance with the test procedure in an unconfined state. So the benefit of stone-on-stone contact or the interparticle friction is reduced because a test specimen is unconfined. However, in reality, mixes are confined as placed on the roadway. So the interparticle friction of SMA mixes does become a benefit, and the stiffnesses are equal or greater than the dense graded mixes, resulting in lower rut depths. Repeated load plastic deformation values are lower than the values measured for conventional dense graded mixes because the test procedure includes confinement. So the test results exhibit the impact of higher internal friction of SMA mixtures. In other words, more resistant to plastic deformation, which means lower rutting. Indirect tensile creep compliance values for SMA mixes generally exhibit more compliance because of the higher asphalt contents and the use of fibers, as well as polymer modified asphalts. Higher compliance values are more resistance to thermal fracture. Indirect tensile strength of SMA mixes, however, are generally lower in comparison to conventional dense graded mixes, generally because of the higher amounts of asphalt. The creep compliance values, however, generally control the resistance to thermal fracture, or creep compliance is more important rather than strength by itself. The impact or difference between the different mixes are going to be illustrated in the next few slides in terms of laboratory measured values. The properties measured in the laboratory have shown the dynamic modulus for warm mix asphalt. Polymer modified dense graded mix is only slightly higher than for SMA at different test temperature, as shown between the two graphs on this slide. The graph on the left, mix 23, is for dense graded warm mix asphalt, but with a polymer modified asphalt. The graph or figure on the right, mix 20, is for an SMA mixture. The observation dynamic modulus for warm mix asphalt, polymer modified dense graded mix is only slightly higher than for the SMA mix. Again, dynamic modulus values for SMA mixes can be higher or lower in comparison to conventional dense graded mixes because the astrodynamic test is unconfined. For this example, the dynamic modulus values for the SMA mixes are slightly lower than for the conventional dense graded polymer modified warm mix asphalt. This slide shows the indirect tensile creep compliance and strength values. The graph on the left is for mix 23 for dense graded polymer modified warm mix asphalt. The graph on the right, mix 20, is the test results for an SMA. SMA mixtures generally have higher compliance than conventional dense graded mixtures, but also have a lower indirect tensile strength measured at 14 degrees Fahrenheit. Specifically, the indirect tensile creep compliance values for SMA mixes generally exhibit more compliance because of the higher asphalt binder content and use of fibers. Higher compliance means mixes are more resistant to thermal fracture. Indirect tensile strengths of SMA mixes are generally lower than for conventional dense graded mixes because of the higher asphalt contents. The creep compliance values, however, generally control the resistance to thermal fracture and are more important than the indirect tensile strength. This slide shows the results of repeated load plastic deformation or strain test. The graph on the left is for a dense graded mix compared to the graph on the right shows the test results, repeated load plastic strain test results for an SMA mixture. The SMA mixture has greater resistance to plastic deformation than the dense graded mix. Repeated load plastic deformation values are lower in general than the values measured for conventional dense graded mixes because this test does have confinement. So the test results exhibit the impact of higher internal friction of SMA mixtures. In other words, they're more resistant to plastic deformation, resulting in lower rut depths. The lower KR1 value, or the larger the negative value from the repeated load plastic strain test, means the more resistance to deformation or rutting in the early life of the wearing surface. The lower KR2 value, the less sensitive the mix is to plastic deformation as a function of temperature. Higher KR2 values generally exhibit higher rut depths, everything being equal, which it is not. The lower KR3 value, or slope, the more resistant the mix is to long-term rut depths. In other words, lower rut depths exhibit higher levels of traffic over time. So in comparison to these two graphs, the KR1 value has a significantly higher negative value for SMA mixes and a lower KR3 or long-term rut depth value. The KR2 value is higher for SMA mixes, meaning more temperature susceptibility, but overall the SMA mixes would result in lower predicted rutting for these laboratory measured values in comparison to the dense graded mixture. So in summary, this is section 5, or a summary of the takeaways in terms of the final discussion. SMA mixes exhibited very good performance and longer service life compared to standard dense graded asphalt mixes, but it is more costly. Many studies have shown that the SMA mixes have much longer or significantly longer service lives. SMA mixes, however, is cost effective, even with the higher initial cost for high stress and heavy duty conditions. The reason for the cost effectiveness is the longer service life, even though the initial cost of the mix is higher. The use of RAP can reduce the initial cost of SMA without significantly reducing the service life, as long as the properties of the SMA have been adequately measured, similar to the balanced mixture design method or approach. It is important to recognize that the aggregate specifications for SMA can be restrictive based on past studies and performance observations, but those restrictions have been found to be cost effective. If the aggregate properties become less restrictive, more local materials can be used, thus reducing the initial material cost, but also generally resulting in a reduced service life of the SMA. The most important one of the takeaways shown on this slide is that SMA does provide and has provided excellent performance and longer service life in comparison to conventional dense graded mixes, and are cost effective, even under very high stress heavy duty conditions. Continuing with the takeaways, the aggregate properties or aggregate specifications for SMA should not be reduced unless the engineering properties of the SMA are measured to ensure the minimum properties and expected design life are being satisfied. The use of SMA mixtures will not improve performance on an inadequate structure for different site condition features. In other words, the lower layers need to be adequate in terms of design and construction for the site feature conditions. In summary, SMA has exhibited excellent performance when designed in accordance with SMA specifications. The most important takeaway on this slide is that if you decide to reduce the aggregate requirement so that local aggregates can be reduced, make sure the performance tests are run to confirm the mixture is still resistant to deformation and fracture. We simply do not recommend reducing the aggregate requirement so local aggregates can be used and or not using fibers or other mineral filler with only using volumetric testing and not including any of the performance tests in making a decision on the SMA mixture design. With that, we would like to thank you for attending this webinar and hope that it was provided some benefit and information for you to use in the future. Thank you.